So welcome to today's webinar on crystal growing in microgravity, protein, viruses, and inorganics. Today we have a few speakers, and what we'd like to do is really give you a landscape, an overview of the work that's been done in low Earth orbit around crystallization over the past, I don't know, 10 years. And I think Dr. Wilson can give us even more insight into that. In addition to Dr. Wilson, we're going to start today by hearing from Dr. Hilda Stenuit, who is IceCube's business development leader for space application services. And she's going to sort of introduce us to what is crystallization and what is some of the work that she's been focused on from a space application services perspective. Hilda Stenuit received her MS in mathematics and applied physics and PhD in plasma astrophysics from KUL, and has worked in operations for the European Space Agency, and since then has been really using her expertise to guide users and create opportunities for commercial access to low Earth orbit. So we're very excited to hear from Dr. Stenuit, from Hilda, right now, and please kick us off, Hilda.
Well, thanks for a great introduction, Cindy. And I'm very excited to be here, and you've done almost all of my introductions. So as you rightfully said, so I have a research background, but not one that is related to proteins or viruses or inorganics or crystallization, but rather to astrophysics background. And so I started working with space application services, and I supported indeed the European Space Agency for quite some years, also in a function of mission science office, coordinating with the different agencies on the different science disciplines on the International Space Station. And now indeed I am supporting our IceCube's service. And for those that are not familiar, our IceCube service stands for International Commercial Experiment Cube Service. So it's in Europe, it was the first commercial access service for research and for technology. And you see some of the pictures of some of the cubes and modules that we fly on a regular basis to the International Space Station for different types of research, different type of technologies. And we provide this service globally. So we work with the European Space Agency in Europe, with NASA and with the ISS National Lab in the US, but also we're very proud and happy to work also with our colleagues from the Japan Manned Space Systems Corporation, JAMSS. And it's one of the partnership collaborations that we're really proud to support, to fly and accommodate this incubator that allows for protein and large molecules crystallization in space. And Sato-san, who's also here with us, will say a bit more about that. So you see that incubator cube that is developed by JAMSS on the left bottom picture, but we'll address it then later on. So enough about me and the service. So I'm grateful to the colleagues from Space Commerce Matters with Cindy and Jose that they proposed to have this webinar. And so the message that we typically pass when we talk to possible users of the service in terms of protein crystallization is that crystals grown in space come out larger and better structured than the same ones on Earth, and they have less imperfections, and all of that can help to reveal the structure and the function of those proteins or molecules more clearly. Now, I have understood that Dr. Ann Wilson and her students have done a retrospective analysis of public domain data of crystals that are grown in microgravity. So I'm surely very eager to learn more from her and on the how and if this indeed supports the value added as we present it and the possible application areas. So with that, I would like to hand it back to you, Cindy, to introduce our main speaker of the day for the keynote.
Thanks, Hilda. Thank you for that. And so, yes, I would like to introduce Dr. Ann Wilson, who is Professor of Chemistry and Biochemistry at Butler University, along with Hannah Wright, Research Assistant. Dr. Ann Wilson is Professor of Chemistry and Biochemistry and is a chemistry professor at Butler University, which is in Indianapolis, Indiana. For 27 years, she has worked with exclusively undergraduate researchers, and after a recent sabbatical with CASIS, she has been performing analysis of research data from the ISS and other NASA programs. In addition to her microgravity work, Dr. Wilson's students engage in analysis of flavors and fragrances in food products, the synthesis of small molecules, and the synthesis of historic dyes. And Hannah Wright, research assistant, graduated from Butler University in May of 2022 with a bachelor's degree in chemistry. She began working on research with Dr. Wilson in 2019 and began working on the meta-analysis of crystals grown in microgravity project in May of 2020. This fall, Hannah, congratulations, will begin medical school in Indianapolis. So over to you, Dr. Wilson, and to Hannah.
Thank you for that very kind introduction. Can everybody see my slides okay?
Yes.
Perfect. In addition to Hannah, I also have Ashley Wilkinson, Amari Williams, and Franny Brewer who have been working on this project. And we have a brand new, we have a young man who's working with us, our token male, and he will be, he's really just started this week. So we're delighted to have the ability to work with undergraduates. And one of the best things about working with undergraduates is that they don't know what they don't know. And so it's been really nice because they collect all sorts of data. And, you know, it's up to us to then figure out the content experts. I don't count myself among them, but to use this data to then find out if there is actually something there. Let's see. We've been engaging in this retrospective analysis where we've been looking at the public domain data of crystals grown in microgravity. We don't claim to have a complete list, as we know that sometimes these particular publications are hidden in journals that maybe we don't expect those particular crystal data pieces to be in. And we also are very aware that there are data that are held as part of IP, so that we don't have everything. That said, what we have been doing is taking the public domain data and looking at it. And the project is supported by NASA, INSPA, as well as collaboration with the ISS National Lab. And we're going to be talking about the data that we found for macromolecules, which are primarily proteins, a few viruses, as well as inorganic compounds with a subset focus on semiconductors. In our crystal database, which is publicly available, there will be links at the end of our presentation. We include in this, so they are searchable parameters. You can download the database to your own computer and do searching based on title, year, number of crystals, as well as specific data points like mosaicity, B factor, space group, applications and conditions. So with this, we hope that we're creating something that would be useful to those of you who are in need of this kind of data. And we're always welcoming feedback as to other pieces of data that should be included in our database. We would like to acknowledge scientific bias that we tend to publish good data and poor data, for whatever reason, we tend not to publish. We try to acknowledge that, you know, there might be some positive data bias, positive result bias that's in our data, as is in most scientific data that's published. I don't in any way expect that you can read this slide. These are the macromolecules that have been subjected to crystallization conditions in microgravity, and it goes on. So, we do have a pretty extensive list. And, we're continuing to add to this list. If we look at the percentages of the microgravity experiments compared to terrestrial crystals, we found that there were 138 microgravity experiments that had a report on size of the crystals. So in this case, we saw that size increased for about 70%, stayed about the same for 12%, and the size was decreased for about 20%. And in many cases, size is not necessarily important if you're looking at some of the other metrics, but there are some impacts of size where you do need a larger crystal, especially for some of the inorganics that we will get to. When we're talking about structural quality, we think that this is a very important metric, and structural quality improved in our macromolecules, our proteins and viruses, for almost 90% of the molecules reported, and this is for an N of 208. For 226, where the data was reported, we saw that resolution was improved for 82%, with 13% not seeing a change and 5% decreased resolution. And we are engaging in a detailed, deep dig into why the 5% that didn't improve. So we will be reporting back on that soon. And the uniformity improved in 83% of the cases. Once again, uniformity didn't improve in 14%. That's another part of what we're digging into for why the uniformity didn't change, if there was some sort of connection between the macromolecules that didn't have an improvement in uniformity. Mosaicity is an important metric for biomolecules, especially proteins, as this will help us determine details about small pieces of the protein chain. And in over 80% of the cases, the mosaicity improved compared to ground experiments, and 14% did not. Once again, this is where we're going to be doing a deep dive and figure out what's going on with the 14% that didn't improve. For our inorganic crystals, we have documented a large number of these, and you can see the ones with that are denoted with the asterisk are semiconductor materials. Once again, I don't expect that you're able to read this entire list and see all of the compounds. I just wanted to give you an impression of the breadth of compounds that we're looking at, for a total of 109 inorganic compounds. And in this case, size for the 56 experiments, that were documented, only about 70% improved, but many of these were parabolic experiments, and so the time that they were subjected to microgravity was very small. So in that case, the size, they may not have had enough time to grow to be a larger crystal. And structural quality improved about 77% of the time, with 15% of the time structural quality not being improved. And we are, again, digging into the ones that were negative experiments. And uniformity improved for 85%. And that this, we think, is really meaningful for this particular data set. Uniformity is, for many of our inorganic compounds, is a very important quality. And here we've combined the data to show for macromolecules and inorganics, the improvement on uniformity, well, size, uniformity, and structural quality. And you can see that the trends seem to be, consistent through all the crystal types. So it doesn't matter if it's a protein or if it's a virus or if it's a semiconductor. Microgravity has demonstrated to show significant improvement in the metrics of crystal growth, regardless of crystal type. We've also done a deep dive into semiconductors. We have 114 semiconductor materials that have been demonstrated to be grown in microgravity. And over the 46 individual experiments with these particular semiconductors, just over 60% improved size. For 73 documented semiconductors, 81% improved in their structural quality, and 83% improved their uniformity. And in this case, none of the uniformity stayed the same. It was either improved or not improved. And as we continued looking at the data that we had, we found that 83% of experiments showed improved uniformity. So that's over 80%, which from an undergraduate standpoint is a good solid B. 89% of the experiments showed improvement in structural quality. 69% of the experiments grew larger crystals than their terrestrial counterparts. And then for the improved resolution and mosaicity, they also were above 80%. If we're looking at just overall, 84% of our molecules showed improvement in at least one metric, 65% showed improvement in two metrics, and 40% showed improvement in three or more metrics. So when you're looking at the combined effects of microgravity, the idea that you can have multiple metrics being positively impacted by growing in microgravity, I think is significant. We'd like to thank Larry DeLucas for insight, especially in his double-blind crystal study. And we've learned quite a bit since then, mostly due to his efforts. We'd like to acknowledge Kevin Engelbert and INSPA for funding this study, and Ken Sabin and Lynn Harper for their encouragement and guidance. And as promised, here are the links. This is recorded. You're also welcome to email me and I can just send you the links, and then you can just click on them rather than trying to have to copy all of these things down. These are freely available, and you can search by all of the particular metrics. So I'm happy to have you all utilize this information and give us feedback, especially if there are other things that you feel that should be included in the database.
Thank you. That was really impressive information. And after we hear from Dr. Sato, I actually have quite a few questions for you. And so now, without further ado, as Dr. Wilson was just describing all of the work done that she has analyzed, these crystallization experiments have been done using various types of facilities and hardware. And now we're going to hear from one of those, which is Dr. Nahiro Sato, who is he's representing the Japan Manned Space Services Corporation, which is JAMSS, which Hilda mentioned. Sato-san studied aerospace engineering and received his PhD at Tokyo University. And then he joined JAMSS in 1997. He was certified as one of the first JAXA, the Japanese Space Agency, astronaut training instructors in 2001. And from 2009, he worked in simulation for flight controllers of the HTV vehicle. And he's been working with the GEM and HTV training and operations for more than 10 years. So now he has sort of pivoted to the Leo commercialization side of the house. He's gone to the dark side. And he is focused on Carrara, which is a service that produces high quality proteins in space to support drug discovery. So what Sato-san will now speak about is one of the ways that we can actually crystallize the proteins that Dr. Ann Wilson just described. So over to you, Sato-san, and I will go on mute.
Okay, thank you very much. This is a great opportunity. I'm now Hirosato from Japan Manned Space Systems Corporation, and I'm Carrara project lead. Here, as Hilda mentioned, that Carrara is a service of protein crystallization on board, and we have the very small cube type incubator. You can see the photo on the right side, and this size is really small, that 10 centimeter cubic. So in this incubator, that we have several crystallization tubes with glass capillaries inside. You can see the photos on the left corner around here. Our first mission was done in 2019, and then now we have already did the fourth missions. Our incubator installed in the IceCube facility of Space Application Services. Our samples came from pharmaceutical companies and research centers. Actually, we also have many other types of samples, not only for proteins, but for example, for the COVID-19 drug research with remdesivir solutions. Well, we did also the cellulose synthesis in space. It was actually first time in space to have successful cellulose synthesis in space. And our last mission was done. It was the first time for us, and it was done using the SpaceX CLS-27. The launch was March 14th, and it returned last month, April 16th. So almost 1 month stay on board. The incubator can keep the inside around 20 Celsius degree for the good conditions of the protein crystallizations. And actually, last time we also have several samples from universities and research centers. And we also provide some STEM program to Japanese students because our sequence of the sequence is very simple. So even the students can do that. Of course, the protein itself is not just lithotrium, so very typical ones, so not difficult to crystallize. But students can have good experience to do the real space missions. And our STEM program was held in Tokyo in February, and the students feed the solutions inside the tubes, and their tubes was launched to the space to the ISS with Carrara in SpaceX 27. You can see the tubes photos on the right side, and this is the crystals actually obtained in space that the students makes. And we have some presentation sessions next month, and they will prepare the report about their studies. We are really looking for that. So like this, we also, of course, our main mission is to support the drug discoveries using proteins, but we also do support the several other types of missions like COVID-19 drug research or cellulose synthesis. These were some organic compounds. And we also do the some STEM program like this. And again, that the students can really do the real space missions with in their experience. And next, Carrara is planned December this year at the earliest. The flight is not fixed yet, but we are now planning to do the next. It should be the 5th mission for us, and will be done in this December. Please visit our website, that Carrara, that is under the JAMSS website, and you can see the other examples of the crystallization, and you can see the more detailed information about this Carrara services. Thank you very much. Back to Cindy. Thank you very much for this great opportunity.
So thank you to all of the speakers. for that. And let's start with the questions. And I would just like to say to Saito-san that we have been supporting his Carrara hardware for a while now, and really seeing some happy customers of that particular hardware with some great results. So without further ado, why don't we start with for Dr. Wilson. Since the size of the organic crystal depends on the time of crystallization, did you observe any difference in the time of crystallization on the Earth and in microgravity?
So from our studies, when we have comparisons, Earth comparisons, they are run at the same length of time, even though we know that that it takes longer to crystallize in microgravity. So when there are these comparator experiments, they are run at the same time. So which means that the crystals grown in microgravity should be smaller size-wise.
Okay. All right. And from the same person we got the question, did you test different solute compositions looking for the size of organic molecules in crystals?
We did not, but we could add that to one of our deep dives that we're going to do and see if there are differences between that. There are several of the crystals that have been run in microgravity multiple times, and it could be that that we could use those as these are, the most beneficial conditions. So we'll definitely look into that.
Okay. Another question, Dr. Wilson, have you looked at crystallization of small molecule organics in microgravity?
Not yet, but I hear that that's in the works.
Good. All right. Another question. Is there any information on the microgravity levels achieved in these different experiments? Also, any information on the effects due to G-jitter that affects the microgravity quality in these experiments or on the final products, crystals, and molecules developed? And that might be for you, Dr. Wilson, or maybe Hilda, you might want to comment on that as well.
I do know that there are some examples of vibrations causing problems for especially for diffusion experiments. And my student Ashley wrote a undergraduate thesis on this, and she found that the experiments that failed often had reasons that had to do with mechanics, not actually the crystallization conditions. So that is one of the challenges of these particular experiments.
Okay, and I don't know, Hilda or Saito-san, if you want to also talk about any of the operational aspects of crystallization in Leo.
Yes, this is Sato speaking. Actually, I'm not a specialist of the protein crystallization. I'm just a space engineer, guys. But my supporters who do this experiment say that crystals itself is very sensitive to temperatures after crystallized. So we try to keep it in the around 20 Celsius degree when returned to the space. And of course, the vibration is not good to start the crystallization. So our colleagues try to adjust the solutions to start the crystallization on board. So it takes 2 or 3 days after starting the diffusions inside, and then theoretically it starts to crystallize after it reaches to the microgravity conditions. So we are very careful about when it can really start the crystal.
Is that one of the services that you do to help optimize the proteins?
Kind of, yeah. Sometimes the crystallization starts very quickly. So if it's to start quickly, that crystals might be obtained before launch or even during the launch vibration. So it's not good. So our support companies try to optimize it to start crystallization on board. I mean in space.
Okay. And Hilda, did you have anything to add there?
So I think that covers that question, but can I sneak in another question related?
Sure, sure.
So on the figure where you talked about the percentages of inorganic microgravity experiments based on size comparison, you mentioned that it's maybe because most of these experiments, I thought you mentioned, were on a parabolic flight and time was too short. Could you give an idea of the overall data and experiments that you considered? How many were on parabolic flight? How many were on space station or other LEO platforms?
So those are all part of the searchable parameters. And, you know, we've not done a classification, these are on station, these are parabolic flights, but we certainly could. And certainly that may or may not have an impact on the data. You know, and those are all things that are worthwhile looking into. You know, we're relatively new to the area, and we've only been doing this for a year. So certainly we're learning that all of these different things, all of these different methods and conditions and time at microgravity are all critical for us to understand how the data can be used and used well.
Great. All right, another question for you, Dr. Wilson. And you're getting lots of thank yous in the chat for these impressive results. So one of the questions, it would be interesting to hear by how much were the crystals larger, better, more uniform? Is it 5%, 25%? You know, what is there a range of that level of improvement?
Oftentimes we give dimensions in the if they've been offered in our database. And from that perspective, we haven't gotten a percentage of larger, you know, is it 1% larger or 5% larger? I agree that those are important pieces of data that we have not dug into. And we're also, you know, depending on the authors of the papers, if they say it's larger, you know, we're going, all right, you know, and we're reporting that.
Exactly.
But we haven't, you know, they oftentimes they don't report how much larger either.
Yeah. Yeah, no, having worked at the ISS National Lab for many years, I understand how hard that is to get that type of precise data. And one sort of follow on from that is it would be great to hear, you know, percent larger, percent improvement, but also what was the ultimate outcome of that improvement? Were you able to, you know,
Right.
like in the Merck-Keytruda crystallization work, you know, there was a clear outcome that could be discussed and what the real value impact is back here terrestrially. So
absolutely.
Yeah.
And we're very aware of, especially with the semiconductors, that the improvement, you know, fewer defects means, you know, a wide variety of applications can be better supported. And we're learning quite a bit about that.
Yeah, exactly, especially on the inorganics when you're talking about a material that has a better performance by 10x or 100x due to less defects, that has a significant impact on that material. So yes, absolutely. So can we ask NASA and CASIS for this work to continue forever, the work that you're doing, because it's incredible.
I think forever is a little bit long, but I'm happy to keep supporting it. And certainly, you know, I have no shortage of students who are interested in working on this project.
Great. Okay, another question. What is the number of experiments you conduct per payload flown? I don't know if I understand that question. And I don't know if that's a question for you, Dr. Wilson, or maybe for Sato-san or Hilda. Number of experiments you conduct per payload flown. I guess that could be for you, Sato-san, or Hilda.
Yes, and per payload means in one Carrara missions, it can contain the maximum 96 tubes. So theoretically, we can do the 96 different types of the experiment on board. That of course, it of course depends on the size of the incubator, I think. So that is our limitation. in our small cube.
Okay, thank you. Dr. Wilson, have you looked into whether room temperature versus cryo data collection might relate to crystal quality improvement or no improvement?
I don't know if we've tracked temperature on the experiments. We certainly for the inorganics, a lot of them were at high temperature, but I don't know if we tracked.
It's probably in the conditions, but we haven't.
Yeah, if it's in the conditions, we would have reported that, but I don't recall seeing a lot of cryo experiments. Maybe, yeah, no, I don't think we saw that many.
Okay.
I've got all my students in here going, shaking their heads.
Okay. Do you have information about the number of protein crystallization experiments conducted in microgravity that lead to scientific publications? And I think this is maybe a follow-on of the outcomes that we were just talking about. So yeah, I don't know.
So we know that JAXA has flown more crystals than have been reported in the literature, but that doesn't mean that there weren't positive outcomes from the experiments. We believe that we've amassed enough data that shows that likely there are improvements, and the improvements are across the board. Because people are reporting some negative results with their positive results. And so we feel pretty confident that there are improvements.
Okay. I was just going to say to that, I know that NASA and the ISS National Lab report scientific publications, citations, patents, that kind of stuff.
Right.
But they do that sort of in aggregate, not necessarily broken down by, the work done in crystallization versus other experiments that are done.
Right.
Okay. Dr. Wilson, where did you get funding to conduct your microgravity research?
Well, I was very fortunate to do a sabbatical with ISS and CASIS and sort of lay the groundwork for this. And then was very fortunate to get connected with Lynn Harper. And so we were able to get funding through pretty much I applied for several grants that were declined because this doesn't fit in neatly into a lot of areas. But thankfully, Lynn was very supportive, and so we've been able to work with Aerospace Corporation, who's funding us, and working with NASA and ISS. So it's been a great collaboration. Undergraduate students are relatively inexpensive, so that makes it an easier sell.
I was going to say, I don't know if Lynn or Ken Saban are on this webinar, but Lynn Harper is an icon. She's legendary. And for those on this webinar that are not familiar with her, she is really the driving force of all of the in-space manufacturing, the commercialization work, just really a pioneer from a NASA perspective. And I was wondering, did you get involved in all of this and through meeting Ken Saban in Indianapolis? Because Ken Saban is also iconic. When I was at CASIS, he was the first person that we went to Eli Lilly, and Ken was running their internal innovation, and the rest is history with all of the prolific work that Ken has done, and Eli Lilly and everybody else. So is that how you got into space?
So Ken and I went to graduate school together. So full disclosure, we went to graduate school together, suffered through organic synthesis together. And then I actually recruited him to Indianapolis. I was already here and he was in the job market, and I said, you need to look at Lilly. And so, the chemistry community is small.
Yeah. And so is the space community. So there you go. All right. A question from Promise Ventures, an early stage space VC fund. Will we be able to access the presentations? Yes. Okay. Lynn Harper is on the call. She asked a question. To the best of my knowledge, there are no parabolic flights reported in the Butler database. They were all or almost all orbital. Thank you, Lynn.
Yes. And Hannah went and did a quick check as well.
Okay, great. Okay, Dr. Wilson, what, if any, were the effects of the temporary hypergravity experienced? Oh, so this is the question on parabolic flights, which we've now said is no. And is there a scope to conduct relevant experiments like these in sounding rocket payloads? These rockets go low altitude, around 10,000 to 50,000 feet, experiencing high G forces and vibrations. And that might be a question more for Hilda or for Sato-san. Or Dr. Wilson, if you have an answer to that. I don't know if that's up your alley.
Not at the moment.
Okay. Hilda, would you have a comment on that, or Sato-san?
Well, I can comment in terms of the microgravity level that people can expect on the different platforms. So I think on the ISS you get of the order of 10 to the minus 5, where on other platforms it can be like a parabolic flight, you get 10 to the minus 2. So that obviously will influence the results of your crystallization. But I don't know if that specifically answers the questions there.
Hi, have RPM microgravity simulators ever been used to test protein crystals?
My understanding is yes, but that was outside of the scope of our study.
Okay. All right. And I had a question as you were presenting, and in terms of, when we saw your data, there was, the B plus improvement, which was the majority across, all crystallization types or compound types. And then there was a no change, and then there was a got worse. And I don't know if I was ever, when I was at CASIS, if I was ever aware of the got worse. Do you have any indication why that happened? And are you looking at the correlation of the compounds that improved versus got worse? And is that what you were talking about earlier in terms of your follow-on work?
Absolutely. We're going through and pretty ruthlessly scrubbing from the data things that had technical issues. So a lot of times the ones that are reported that got worse were because of a technical issue. Something didn't work right, something wasn't injected properly, that sort of thing. So we're scrubbing that from the data. And sometimes that takes actually contacting the author of the study and finding out, what was going on with these ones that were reported to be worse. So, and individually, that could be, some of the things that are going on. And we're having to do, individual crystal by crystal practically to find out what's going on with some of the ones that were reported to be worse. And then there are others that, perhaps the conditions weren't optimal or those sorts of things. So those are the kinds of things that we're trying to find out. There are many crystallization conditions where, they were setting it up for a bulk study. And that may not be optimal for one set of the crystals, but it's really good for the other set of crystals. And so those are the kinds of things that we're trying to pull out of the data, especially with the ones that were not as successful as their counterparts, and see if we can't, demonstrate a lessons learned. These are the things that
Yep.
one needs to do if we want to grow crystals in microgravity.
I think that would be helpful. And the last question is, did you look at the type of process used, whether it was vapor diffusion or counter diffusion or batch or whatever, and is there a correlation of the type versus the results?
At this point, my student Ashley wrote a thesis. Her undergraduate thesis was basically about all of the diffusion experiments for protein crystallization, and there isn't a difference between all of the different diffusion methodologies. It is statistically significant difference. There's none. So at this point, we haven't looked at beyond diffusion experiments, which are the majority of the experiments for protein crystallization. We haven't looked at other kinds of crystallization techniques to see if some of them are, just generally better and that sort of thing. But we will be looking into that as well.
Okay. So we have a question for Sato-san. How did you extract the crystals from the capillaries? Do you extract them at all or just mount the capillary to the goniometer, which I cannot pronounce?
Yes, thank you very much. Very good question. That in Carrara, our mission that we use a counter diffusion method using capillaries. So inside the capillaries, there is a concentration gradients inside. So our specialists carefully analyze the concentration of the solutions and break the capillaries in appropriate position, and then pick up the crystals. So actually, to pick up the crystals, we have to break the capillaries and carefully put it into the solutions, not to damage on the crystals. And we also have them do the neutral analysis. We sometimes make the crystals for neutral analysis. In that case, our capillary is made of quartz. So theoretically, there's no need to break the quartz capillary. They can just put the quartz capillary to the detectors. So it depends on the type of the crystals. But anyway, for the generally that we have to break the capillaries to pick up the good crystals from inside.
Interesting. Okay. Lynn is asking, can we get a copy of Hannah's or Ms. Wright's thesis?
Ashley Wilkinson's thesis, and she would be happy to share it with you because it will soon be out on the university commons. So it will be posted, but I'm happy to share a digital copy with anybody who would like to email me.
Great. And I think we're starting to wrap up the questions. Did you test the biological functionality of viruses after microgravity tests?
I didn't do any of these studies. They would be, so if you search the database for viruses, you can find the links to the actual papers, and you can find out if they did that.
Great. Well, I think this is a nice time to end this session. I was very happy that we had so much time for so many great questions and discussion here. And I, for one, am very excited to see your work continue, Dr. Wilson, because I think this is really, the type of information that we need to really prove the business case of why space and why should a non-traditional space terrestrial industry do crystallization in space. So hearing from you, sort of with no skin in the game, just looking at the data, I think was very, really powerful today. And thank you to Hilda and to Sato-san, and really with your experience doing this work in space for the last, how many years, 10 years of commercial activity, I think is really coming together now with, we're seeing that there are tangible benefits to doing it in space. And folks like Hilda and Sato-san are the folks that are actually making it all happen. So thank you all for participating today. Well, again, thank you to everybody on all of these different time zones for participating, and really, really exciting webinar. Thanks again, and take care, everybody.